Hello, everybody. Welcome to the 6th Flow Seminar. My name is Samuel Horvat, and I'm a PhD student at KAUST, and I'm one of the organizers of the Flow Seminar together with my supervisor, Peter Victarik, Virginia Smith, Avrelin Bellet, and Dan Alistar. Yeah, for those of you who are attending for the first time, let me give you some information about the seminar. So Flow Seminar stands for Federated Learning One World Seminar, and it was created as a global online forum for the dissemination of the latest scientific research in all aspects of federated learning. This includes both theory and application, and areas such as distributed optimization, learning algorithms, privacy, cryptography, personalization systems, hardware, and many more. So for today's talk, we are very lucky to have Hadrien Hendrikx as our speaker. So Hadrien is a PhD student under the supervision of Francis Bach and Laurent Massolier at INRIA and ENS in France. So prior to that, he graduated from École Polytechnique in 2016 and got a master's degree from EPFL in computer science in 2018. In his research, he mainly focuses on asynchronous algorithms for decentralized optimization. And today he will talk about statistical preconditioning for federated learning, which is based on his very recent ICML paper with Lin Shao, Sebastian Bubeck, and both of his supervisors, Francis and Laurent.
Well, hello everyone. The people haven't changed, and so today I will talk to you about statistically preconditioned methods for distributed optimization. So I'll dive into the setting. So as I said, we would like to solve a distributed problem. So on the one side, we have a server which holds the parameter of a model that we want to optimize. And on the other side, we have the clients which hold the data. So basically, the data is distributed among many instances, and we as a server want to learn from this distributed data. So this can be either because the data set is just too big to hold on one place, or because the data is just inherently distributed. It's collected by cell phones or hospitals, and they don't want to move data around, or just because moving data is generally expensive. So many reasons for this model. I'm sure all of you are aware of it. So the problem we would like to solve is a distributed empirical risk minimization problem. We want to minimize this function capital F, which writes as an average of smaller functions fj. And so you need to think of fj as the local function of node j. So in our setting, we have m worker machines, and each machine has its own loss fj, and fj is basically the loss function on the local data of node j. And what we would like to do is to minimize this average, so it's in dimension d, and it really corresponds to a typical machine learning model. So to minimize this problem, we will adopt a centralized communication model. So as I said, we have the server on one side and the workers on the other side, and the data is at the workers. The server has no data for now. And so how this will proceed is that the server will first broadcast the parameter to the servers, to the workers, and then workers, they compute a gradient. That's basically the only thing that they can do, compute a gradient. And then there's a big reduce operation going on, and the server will get the global gradient of the function and just perform a standard gradient descent update. So xk plus 1 is xk minus a step size times the full gradient. And then once the server has computed xk plus 1, it broadcasts it again, and it continues like this. So the important thing here is that each iteration requires back and forth communication between the server and all workers. So the communication complexity is really limited by the iteration complexity of the global method, and we would like to reduce this. So what we will do is that we will assume that the server actually also holds some data. So the server also holds a function fn, which approximates the global objective in some sense. So all of this will be made rigorous later. But now the data is not only at the workers, but the server also has some. So the server also has an idea of what the global objective function looks like. So it doesn't want to just optimize this. It doesn't want to optimize its own function, but it knows a bit like what the cost function looks like. So the model will still be the same as before. So the server broadcasts the parameter, the workers, they compute just the gradients, then they just give the gradient back to the server. What changes is really the update. So we will want to do at the server things that are different from just gradient descent as we used to before. Yes, sure, I'll remove the chat from the screen. But then I can't see the chat. Okay, well, so now I can't see the chat. That was the last question. And so our goal will really be to use this function fn at the server to perform better quality updates and reduce, hopefully, the communication complexity. But the objective doesn't change. The data that we want to optimize is still at the worker, but we have a different data sets, which is smaller at the server, and we want to leverage it. So do you have any question on like the global setting or direction this is going to? And I don't have the chat, so maybe.
I will notify if there is some question.
Okay, thank you.
So at the moment, there seems that everybody is clear on this. There are no questions, no raised hands. We can continue.
Cool. So now I'll give a small outline. So first of all, the notion of how well a function is approximated by another, we use the notion of relative smoothness and strong convexity to make this a bit more formal. And we'll actually reduce this like approximation quality to a scalar quantity, the relative condition number, which we note kappa f over phi, which is like how function phi approximate function kappa. Then the rest of the talk will be devoted to evaluating this quantity. So kappa f over phi, this relative condition number, how big this is, because this will be the central quantity that our algorithms will depend on. And in the last part, I'll give an algorithm which basically achieves square roots of this relative condition number iteration complexity and thus communication complexity. And hopefully, if this relative condition number is smaller than the usual one, then we would have won things. So just as a warm-up, I'll start with the basic gradient descent iterations. And so it's a very natural first-order method, and it writes like this. You have xt plus 1 is xt minus a step size times the gradient of the whole function at points xt. And to prove convergence, you need some assumptions, and a set of assumptions that's very convenient is to assume strong convexity and smoothness of the function f. And this means that the Hessian of your function is lower bounded by a constant times the identity, and it's upper bounded by a constant, another constant L times the identity. So this one is strong convexity constant, this one is smoothness constant. And if you choose your step size as 1 over the smoothness constant, then you can show that in order to achieve error epsilon with these iterations, then you need roughly kappa f log 1 over epsilon iterations, where kappa f is the ratio between the upper bound on your Hessian and the lower bound on your Hessian. So this is quite standard optimization. And actually, this is not the fastest you can do, and you can accelerate gradient descent. The algorithm is really not much more complicated. You just add an extrapolation step, and you get an algorithm that depends on the square root of the condition number. And actually, that's optimal. So you can't do better than square root of the condition number if you only have these strong convexity and smoothness assumption. And now I'll just like quickly try to give some intuition why this is the limits. And so these two plots, they're the lines, dark lines are the level sets of a function f that we would like to optimize. And the blue line is the trajectory that our algorithm takes. So we're here, and then you take a gradient step, you end up there, then you take another gradient step. And the gradients, it's orthogonal to the level set of the function. And you see that when the function is ill-conditioned, actually this means that the function grows much faster in some direction than in others. And so the level sets, they will look a lot like ellipsoids. And so in this case, if you take a gradient, then you know that if you take a very small step, you'll get closer to optimum, but you're very likely to overshoot. And the line that you will draw, it will not go through the optimum at all. In the well-conditioned case, when the condition number is small, the level sets of the function, they're pretty much circular. And so if you if you follow the line given by the gradient, you likely end up much closer to the optimum, and so it's much easier to optimize. And so that's basically why we have this limitation on gradient descent. And now the idea of this work is to change the geometry of the problem, because in the end, like all this condition number thing is really about the geometry of the level sets of the function, and it's purely Euclidean. And what we would like to do is to take advantage of the proximity assumptions between our function fn and the function capital F to go beyond this lower bound and break this lower bound. Because if we know using the function fn, if we have an idea of what the level set of the function look like, even though they're not the exact same ones, then this will give us information, and this will allow us to optimize much faster. So how we do this is we first reformulate the gradient descent iteration. So it can be formulated in an equivalent form as just minimizing the dot product between the gradients plus some quadratic terms. So it's minimize the dot product with the gradients without going too far from the original point xt that you come from, where the distance with your original point xt is calculated with the Euclidean distance. But actually, you don't have to have this Euclidean distance. And if you introduce the Bregman divergence, so it's always relative to a function. So the Bregman divergence of a function relative to a function phi between x and y writes like this. It's phi of x minus phi of y minus the gradients times x minus y. You already see that the Bregman divergence, if phi is convex, then this will be a positive quantity. And actually, you can minimize the following problem. So it's just you replace the Euclidean distance by Bregman divergence between x and xt. And doing this, you've already changed your updates, and you've kind of changed the geometry of your problem. And if you take, there was some problem. So if you take phi, which is equal to just the squared Euclidean norm, then you actually get back to the GD iteration because the Bregman divergence is just the Euclidean distance. And so now just the properties of mirror descent. So you also need assumptions, and they're actually very close to the assumption for gradient descents. It's just that you need a relative smoothness and a strong convexity. So before we had this Hessian of our function f, and we wanted to lower bound it by a constant time identity, and same for the upper bound. Well, now instead of a constant times identity, we take a constant times the Hessian of our function phi. And that's really the only difference. And actually, if you take phi is equal to the squared Euclidean norm, then it actually comes down to the same thing. So you recover the usual definitions of strong convexity and smoothness. And so if you're equipped with this slightly different assumption, then you can actually prove the same results, which is that your method will converge in kappa f over phi log 1 over epsilon iterations. So basically, if you change your iterations and you slightly change your assumptions, then you get the same thing, but with a different condition number. And that's exactly where we wanted to go. And the idea is that hopefully, if you choose phi in a smart way, then this new condition number will be much smaller than the original one. And by doing this, you will have gained iterations. So that's the basic ideas. And now, like the two questions that we'll try to answer is what phi should we choose? And well, obviously it will involve our function fn, and what's the corresponding condition number. And then we'll talk a bit about acceleration of this mirror descent method that I showed you. Is there any question at this point?
It seems that everything is clear. I guess you can continue.
Perfect. So now it's the disclaimer slide. So what I presented you is not it's not something that we invented. It doesn't come out of thin air. And actually, there's this very nice paper by Ohad Shamir, Natis Rebro, and Tong Zhang, in which they develop a similar idea. And so they give an algorithm which is called Dane, and in which you take a node. So it's the exact same setting that I presented you. So nodes compute their own gradients, then they communicate to compute the global gradients. But the difference is that each node actually computes a local mirror descent step with respect to a function phi I, which is the local function plus some quadratic term. So basically regularized local function. And then the global updates is computed by averaging all these local steps. So it's pretty close to the mirror descent update I showed you. It's just that each node does its own mirror descent update, and then you average the results of everyone. So it's a bit computationally intensive because each node solves a subproblem. So
no. There is one question from Tim Don, so maybe you can go ahead.
Oh, okay. So do you have some intuition or explanation about the relative smooth assumption or relative strongly convex assumption?
Yeah, so basically it's about, so for the, so strong convexity says that you must grow faster than a quadratic function. Basically, like if you have like how you explain it to people, it's just you draw the graph and you say that at each point you should be able to draw a quadratic function that goes faster than this one. And really relative strong convexity and relative smoothness, it's the same thing. It's just that instead of just a quadratic, then you should put the function that you want to be smooth relative to. And so it can, yeah.
Sorry. So if I have the function like only like the original definition of strongly convex function grow quadratically, then mere descent in the strongly convex case may not be applied, right?
What do you mean? Sorry.
So if the function f is not relatively strongly convex, for example,
yeah,
then mere descent in this case may not be applied. I mean, like that's the optimal rate.
It can be applied. It's just that you won't get this rate. So I presented this version. Then you have like plenty of versions of mere descent. Same thing as gradient descent. I presented for a smooth and strongly convex setting, but you can apply it for non-convex setting. You can apply for weakly convex. You will just get different guarantees, basically. So it's the same thing. Like it will work, but you will get different guarantees.
Thank you.
And it's not necessarily stronger or weaker than a strong convexity. It's just a different notion. So people use it either with more restrictive function phi or at the inverse, easier function phi to verify. So yeah, the Dane algorithm is really like, it's very close. Unfortunately, it has rather high iteration complexity. So of order relative condition number squared. So it wasn't framed in these terms exactly. So here I'm like putting the terminology I introduced, but basically that's what they prove. And they had a lot of follow-up papers. So it's really an interesting algorithm. I think Peter, you were on one of these follow-ups. And that was really our starting points. And so following them, we just use the mere descent updates, but with the function at the server. So now we don't want each node to optimize, so to solve the mere descent step with respect to its local function, but we have a server that has a local dataset that can be different, and the local dataset of the server can have no overlap whatsoever with the other functions. And so what happens is that the server solves the mere descent step with respect to this phi, so it's regularized local function. And the rest of the algorithm is the same. So really the nodes, they just compute the gradient, they send it to the server, and the server just does a slightly more complicated update. And that's like really the heart of this statistical preconditioning thing. It's really just this, is change the way you update things. And if you choose phi wisely, and wisely is just your local function slightly regularized, then everything goes well. So again, this was kind of present in the Dane paper at the beginning. So they give an analysis for this algorithm in which like only one node performed the updates and not all nodes, and then averaging. It's not the same terminology, but it's really the same kind of assumptions. But then they don't investigate more like what do we need for these assumptions to be verified, like what's the relative condition number, when does this happen, can we accelerate it? So they just kind of put it like this, say that if only one node does it and you have like these favorable assumptions, everything go well. And so then we ask, well, that's kind of interesting. So how, like, what are these constants? Can you relate them to the actual condition number? And can you do faster than that? Can you accelerate these algorithms? So that was like we really started from this, and then we started asking these kind of questions. And so now I'll talk about how to bound this relative condition number. So I'll start with the quadratic case. So our function f, capital F, is just a mean of quadratic function. So it's just regularized ridge regression. And the function fn is just the same thing, but with less samples. And you don't really need them to overlap. We just assume that they are IID from the same distribution in this work. And actually, if mu is chosen such that the supremum of the distance between the Hessian is smaller than some constant mu, and this is how we will want to set the mu for the phi function, then you can have like a very easy math give this bound on the relative condition number. So the relative condition number is basically of order mu over lambda, where lambda is the regularization you have, and mu is the bound on the distance between your Hessians. Turns out that if your objective is quadratic, then your Hessians, they don't depend on the points at which you compute them. And so this can just be bounded using matrix concentration bounds. So you have like a very good monograph from Trop on this, Joel Trop on this topic. And you can really use these bounds out of the box, and you get mu, which is equal to roughly r squared over square root n, where r squared is the bound on the norm of the AJ. And so what you get is kappa f over phi, which is roughly the original condition number, but divided by square root n. And so you're already kind of happy because you've already won a square root n factor. And this is really all painless. I mean, I didn't describe it, but it's very easy. You only have very few steps each time, and it works very well. But it turns out that you can actually use relative bounds instead. And so if you don't try to bound this supremum directly, but you go, so you know that you don't actually want the supremum. What you want is the control on the Hessians. And if you have this in mind, then you can write the concentration bounds in a relative way, so apply it to these rescaled samples, and it's slightly more painful, but it's still pretty okay. And if you adjust your alpha and beta well, what you get is basically this. So this means that your relative condition number, it will still be so 2 divided by 3/2 plus 2 mu over lambda. So basically it will be mu of lambda again. So same thing as before. But now what is interesting is that your mu can be much smaller than before. So mu now is of order r squared over n instead of square root n. And so you have a log factor. You already had a log factor before. I just didn't mention it, but you have a log factor in the dimension and in the probability that this holds. But basically, the take-home message from this is that if you do things a bit more carefully, and if you know what your true objective is, then you can derive kappa over n instead of square root n. So you get a much faster decrease in the number of samples of your function. So recall that n is the number of samples of the server's dataset. So not the whole function, but the smaller dataset at the server that you use for preconditioning. So that's the story for quadratic. Any question on this?
I have a question.
Yeah.
So clearly there, one can think of a scenario which I think you don't have in mind, but one can think of the scenario where these workers have minimal amount of data and there's lots of data on the server, and nothing prevents the server to simply just collect data on their own.
Yeah.
And if we go in this limit, then essentially we're back in centralized training, where the server is just trying to optimize using its own data, their own model, without any federated, almost any federated anything, because there'd be much more data on the server. So what do you get in that regime, which is not the intended regime, I believe, but what do you get in that regime out of this? How should we think of it?
Okay, so here, a key point is that the function at the server, it does not change where the optimization is going. So you will still optimize only on your workers' datasets. You will not change the objective at all. what will change is the speed at which you optimize. So the number of iterations that you require, and but performing these iterations, you will go to the same place, but just you will probably go slower if you have a different function, or it's really like you won't change the objective, and the only important thing is that you approximate the objective in some way, but it's only important for speed. You don't change the optimum whatsoever. Have I answered the question?
Yes, it's partially yes.
So
Thank you.
Yeah.
Yeah, we have one extra question from Anas Borakat. How do you choose N?
How do I choose N? Okay, so N, I mean, I choose it like as large as I can. I mean, the better the N, the happier I am. It's just that N is basically what your server can handle. Like, can you collect 10 million samples at your server, and can you pay the price at each iteration to do this preconditioning with that many samples? So basically, N is like, we would like it to be as big as possible. It's just that then in terms of hardware cost and stuff like that, it becomes more expensive.
So can I ask a question, a follow-up on that what I asked? So
yeah, sure.
So the follow-up question is here this. So I understand that you use this data on the server as a preconditioner, but in fact, if you collected a lot of data, since you assume it's coming from the same distribution, right, as the data on the workers. So, but if you had enough data on the master, then you could decide, if you wish to not use it just as a preconditioner, but to simply model the problem itself and just solve it there.
Yes.
So in some sense, you make a decision to not think of it as a good approximation of the function, but as a preconditioner. So can something be gained by thinking of it also as approximation of the, why do you decide to collect the data? It's coming from the same distribution, and then say, I throw it out if in fact this is more data that you can train on.
Okay, so
the server could be thought of as n plus
to train on
first.
as well.
Yeah.
So you can decide to train on as well. And it's really a good baseline to initialize on, like, just solve your own problem. And that's actually like how I initialize the algorithm in the experiments. It's just like the server starts by solving its own problem. And then like that's already, if you believe in statistics, a good baseline. But the idea is that you would like to also enrich your view of the world using the workers. So this is really like you know, it's a good baseline, but it's just not enough for you. And we'll see in the experiments that if you take n to be, for example, 1,000, whereas there are like 10 million points in the data sets, it's already a very good preconditioner.
Yeah, sure.
So
okay,
like there are really orders of magnitude between small n and capital N. That's really like where we want to gain.
Okay,
so we have one extra question by Jingfeng Wu. I can try to either unmute you or I can like read it loud. So the question is possible to extend this argument.
I'm sorry, I didn't hear you. There was
the question is that is this argument for the conditional number can be extended to the general case, like convex loss function? For example, can you use some like union bound for the x?
Yeah, that's the next slide.
Okay, cool.
So I'll continue. So so it's not the general convex case, it's generalized linear models. So it's like logistic regression, for example, that's like the big use case we have in mind. And so in that case, we don't have a quadratic, but we have a loss function applied to dot product between some sample vector and our parameter vector. And in this case, we will go the supremum approach. So we'll bound this supremum and use it to derive the bound and the condition number. But the problem is that now the supremum does exist. So your Hessian does depend on the points you're at. And this is a big problem because you want concentration to hold uniformly in X, not just pointwise. And if you use matrix concentration bounds, then you only get pointwise convergence, and this is not enough for your problem. So actually, one way to do things is to just pave the space, and I believe that's what the person asked the question mentioned. Like you can just, so you have a domain D, and you can just like put a grid on your domain, and if your Hessians are Lipschitz, then you say that wherever you are, you're never too far from a vertex of this grid. And so if you do a matrix concentration bound at each vertex, and then you do a union bound, then you're not too bad, because basically when doing the union bound, you will pay a log factor in the number of vertices of your grid. But the problem is that there are exponentially many vertices in the dimension. So the number of vertices is exponential in the dimension. And so you pay an extra D multiplicative factor. And this kind of defeats the purpose because, I mean, of course, sometimes D is small, but usually for these kind of problems, like interesting linear models, D is very, very big. And so you don't really want to have this extra D multiplicative factor. And so what you need to do in this case is something that's a little more complex. And you want to directly prove concentration of the supremum. So I'll go quickly over this slide. I mean, the formula is a bit barbaric, but basically the idea is just replace the operator norm by a supremum over the unit ball of phi 2 of AI transpose X, where phi 2 is just the squared norm. And here you can think of phi 1 as the second derivative of the loss. And so you're down to evaluating the concentration of this variable y. So concentration of supremum, there is a literature about that. So you can use, for example, McDermott inequality, and then you want to bound just the expectation of y, and you do that during symmetrization and Sudakov lemma. So I'm really not going into the details of this analysis, but this first approach, it works. It gives you mu, which is roughly r cubed over square root n, which is not too bad because it recovers the first result that we had in the quadratic case. And it's quite simple. It means once you have the steps, they follow naturally. You have a bit of math in between, but the approach follows well. If you want to go further, you can use chaining arguments. So this basically consists in using infinitely many pavings and looking at the difference between each level of paving. And if you have a sub-Gaussian assumption on your AI, and you assume that n is not too small compared to d, then you can get back the r cubed over n that we had before. So we just add, before we had r squared, we just add r cubed because of this, of the fact that we have a function now. But so basically we recover our 1 over n dependence. But this second proof is much more involved, and you have some extra assumptions along the way. So they're not very strong assumptions, but you do have more assumptions along the way. And so yeah, basically the message of this is that you can recover the quadratic bounds, the 1 over n decrease in the general, well, in the case of generalized linear models, it's just more complex. But yeah, things still hold, and that's great. So in the end, you gain a 1 over n factor, so you replace kappa by kappa over n all the time, so not just for quadratics. That's nice. So any question on this? And this is quite technical. Maybe not the best place to present.
There seems there are no other questions, but I would have one. So,
Yeah.
so do you see like this to be extended to like a general convex case? Like, do you see hope?
I think then it really depends on like the kind of assumptions you have, like the structure you have on the functions. Like the linear model is really convenient because you can decompose it as like this sum of this product, sorry, of functions of linear products, and then like basically everything goes well. Beyond that, I'm not sure. I mean, I'm sure there are some favorable structure, and if you have like a favorite problem, then I would be surprised that you couldn't prove equivalent things for your favorite problem. But I think it's a bit hard then. Yeah. Yeah, that's really structure dependent here. Okay, so now I quickly go over the algorithm. I don't want to be too long on this. The idea is just if you want to do acceleration, the algorithm is not so different. So the mirror descent step is replaced by this step, in which basically instead of minimizing, instead of penalizing the distance to a point VT, then you penalize the divergence, convex combination of divergence. But this is not more complex to do in general. So you have like similar complexity and then just convex combinations. And remember that everything happens at the server. And like our goal is really to reduce the communication complexity. So this is like only pure local computation. You don't need to communicate for this. I mean, don't need to communicate more than in the previous case. So that's nice. And the only problem is that you need a sequence GT that verifies this kind of formulas, and this is related to the convexity of your Bregman divergence. So the problem is that the Bregman divergence of the function phi is not convex in the second argument in general. If it were, we would have no problem, but usually it's not. So we have problems with acceleration. And so assuming this, and I come back to this later, you have pretty good acceleration. And you only need to communicate to compute the gradient. But as I said, the crux really is in the GT, and you see this in the rate. So with the algorithm I showed you, the rate is basically like the error decreases as the product of 1 minus square root of the relative condition number. So we're happy about this, but times the square root of jk. And so if jk were equal to 1, we would be very happy because we would have actual acceleration. But in general, all we know is that jk is smaller than the condition number of our function. And this can be much, much bigger than 1. So that's not great. But then again, what's saving the day is that if your Hessian is Lipschitz, then GK goes to 1 when the algorithm converges. So you won't have, at the beginning, GK may be high, but as optimization progresses, and we know it progresses because we have an upper bound on GK. So as time goes, we know that xk converges to x star. We even have a speed, and we know that when this happens, this gain gk also decreases. So eventually, we do hit the kappa f of phi rates. So about this, it's possible to choose jk equal to 1 for quadratic objectives. So in the quadratic case, it's true acceleration. In the general case, we only have eventual acceleration, but actually it seems maybe not impossible, but at least very hard to go beyond that, because there's actually a lower bound proven by Dragomir et al., who show that actually you cannot accelerate mere descent that easily. So if you only, well, they don't, they're not in the exact same setting, but basically the idea behind the work is that this kind of eventual acceleration phenomenon is bound to be. So if you don't have extra assumptions, you need to pay that. And we have extra assumptions, so we may be able to work around this, but basically like this is inherent to using mere descent type methods. So now I quickly go over the experiments. What I solve is a logistic regression on the RCV1 dataset for this example. And the different colors, therefore different values of n. So here it's a typo. The red one is 10 to the 5. And so the orange lines are for 1,000 points at the server. The blue ones are for 10,000 and the red ones 100,000. And we have 500,000 in total. So you see that for the red one, you have like 1/5 of the whole data set at the server. And what you see in this case is that optimization is really fast. In a few steps, you're done. So in dark, you have accelerated gradient descent. So accelerated gradient descent is rather slow. If you have a lot of data, then basically you're going very fast and the acceleration doesn't matter. So the solid line is Dane. The dashed line is SPAG, our algorithm, and the dotted line is a heavy ball acceleration of Dane, which was done by Yuan Li, and that enjoys not exactly the same, but similar, I'd say, convergence properties. And so we see that the two accelerations are more or less the same. And then when you have a lot of data, you go to the optimum very fast. But when you have less data, then acceleration does help. So you do win a lot by accelerating. But it's just that here, n is more important than the kind of method that you use. I mean, you'll gain more by using a larger n than what you would by using an accelerated method. If you go to more complex data sets, such as KDD 2010, so this one is much, much bigger. You have about 8 million points in dimension 20 million, which was a very small regularization parameter of 10 to the -7. And so now the rest is exactly the same thing. And now you see that you do observe some overlap. So at first, if you don't have so much data, like if you have 1,000 points, so that's not even 1,000th of the whole data sets, then actually Dane is going to be rather slow, at least slower than accelerated gradient descent. And that's also because it's not an accelerated method. So you will pay the very small regularization as well. But as soon as you get more samples, so you really see a break-even point at 10 to the 5, at some point, you really have enough data for this statistical preconditioning to matter and to really make a difference. And here, we also really see that acceleration in practice, it does help. So in the blue curve, it's really striking. Without acceleration, the method is much slower than accelerated gradient descent. But when you add acceleration on top of that, you're as fast as if you were preconditioning with 10 times more samples. So you really want to use both a large N and acceleration, but if you can't afford large values of N, because the bigger the N, the better, but you can't always afford to have big ends. So in this case, acceleration really saves the day, as we see on the blue curve. I just skip this slide. Just quickly, so our main contributions are really to link these statistical preconditioning ideas that were really in the air to this principal convergence theory based on mirror descent and to this relative condition number bounds. So it's not just like say that if functions are close, then you get this, but really in characterizing how close they are depending on how many samples you have, and provide acceleration, which is asymptotic in theory, but really effective in practice. Of course, there's still like some problems around understanding really GT and the asymptotic nature of acceleration. But I'd like to go towards the more federated learning aspect of things.
There is one question.
Yes,
yeah,
sure.
So Mike Rabat is asking whether in these experiments does the data at the server overlap with the data at clients? So if you could go back to your experiments.
Yeah. So in this experiment, they overlap. They overlap, but as I said, you have like, for example, for the orange one, here you have 1,000 points. Here you have about 10 million points. So you have overlap, but it's not like, it's not a significant share of the whole data set.
So I would ask a follow-up question on this.
Yeah.
So what do you, I presume you work in the IID setting, right? So all the clients have the same, I mean, not the same samples, but samples from the same distribution.
Exactly.
And so when you work with the KDD dataset, I assume you just permute and randomly partition,
exactly.
Correct?
Yeah.
Okay. Do you have any ideas how to extend these ideas to the heterogeneous data setting, which is so important in federated learning?
Well, again, you don't need to have like this IID. So the IID setting is just like for our bounds to hold. So the bounds that we give on the relative condition number, they depend on whether it's IID or not. If it's not IID, then you don't have the bounds, but you can still run the algorithms. You can still evaluate experimentally your parameter mu. And in this case, I think acceleration really pays off when you have heterogeneity. Because here, for example, in the red line, acceleration, it doesn't help because the dataset of the server is so close to the datasets, to the global datasets, that you don't really care about accelerating because you already know where you're going. Now, in the case of heterogeneous datasets, then since your relative condition number is much higher, then you will really benefit from this acceleration.
Right, but how should we think of the statistical preconditioning in the heterogeneous setting? So what distribution does the server have samples from? Because these clients, they have their own distribution. So is it some kind of a mixture? What is when would that work?
Okay, so that's a bit related to what I wanted to say now is that so preconditioning data, it does not need to be a subset of the training data. And you only need to look like the training data. For example, things you can do would be to make differentially private transformation of your data and just send this data. And of course you add noise to make it private. Of course you add stuff, but in the end, it's not really a problem because you're not optimizing on this. You're just using this to go faster. So you can add all the noise you want. I mean, not all the noise you want, but you can add a lot of noise without perturbing the objective. And I think in the differential, in the federated learning setting, in which you really want to keep your data private, well, either the centralized entity can come up with some data sets. I'm not sure how it would do that, maybe some trusted peers, or I don't know. But really what you can do is like add a bunch of noise to your own data, maybe a flip level or your like preferred way of curating data, send this to the server. And as long as it's does look a bit like the global cost function, then it will be okay. I think that's really like the power of this thing, that you don't need to be a subset and to be the exact same thing. You can perform like a private transformation and stuff like that. It's completely allowed. And
thanks.
In the trade-off, you don't lose precision, you just lose speed. And so that's I think an important feature as well, that you will go to the same objective. It's just that you may be a bit slower on the way in. That's acceptable, I guess. And now for some perspective, it's just well, of course, what I presented works with the full gradients. I think having stochastic gradients is almost mandatory, but luckily it should also be very easy to do because the framework is well established, it's well understood. Once you cast things as just mirror descent, then stochastic mirror descent is something that exists already, so you can just apply it and it should work, I mean, almost in a straightforward way. So once you frame, and I think that's also one of the key things, that once it's framed like this, then you can extend it very easily. Also the inexact inner problem solving. So our paper is like the ideal world scenario in which we solve problems exactly. In practice, you can't do that. So there are works that deal with this for Dane. So I think this could be like extending this work to this setting could be nice. And also there's still the problem of tuning the parameter mu. We do give like heuristics for this, but at the end of the day, it's a bit like a step size. You need to tune it a bit. So yeah, I'm done. Thank you for your attention.
So thank you very much, Hadrien, for your great talk. Are there any other questions or comments?
So I have another question while people are thinking what to ask. So, and in the theoretical part on acceleration,
yeah.
So I understand that you have this inequality, which somehow looks like, the inequality at the top, which somehow looks like the triangle scaling stuff. Can you comment on this and the relationship to that?
It's exactly the triangle scaling stuff. It's just that you add a gain so that basically you know that it doesn't respect the triangle scaling. So you add this GT to compensate for this. It's like you can add, you have a slack by GT and you will pay basically the slack that you allow in the convergence speed. But it's pretty much the triangle scaling inequality, yes.
Thank you.
And if you do, I think we didn't do it in the end in our paper. We just kept with this exponent 2. But actually, the math goes through if you want to use other exponents and other functions phi. It just was more complex and didn't help the message much. But yeah, it's so related that you can also use like this gamma exponent and all this stuff goes through.